All right, great. Yeah, so I'm really excited to introduce He. She's an assistant professor in the Center for Data Science and Current Institute at NYU, New York University. Before that, she spent a year at Amazon and was also a postdoc at Stanford. She got her PhD from the University of Maryland, College Park. He and I were lab mates there and had the same set of advisors and now basically work on the same problems as well. So broadly, she's interested in machine learning and natural language processing, and her current research interests include text generation, dialogue systems, and robust language understanding. So yeah, take it away.
Yeah, thanks for the nice introduction. So I'm very happy to be here today and talk about our recent work on robust natural language understanding. And this also includes some very recent work. So I would love to hear your feedbacks. And as Neha mentioned, feel free to interrupt in the middle, or I can also just read from the chat window. Okay, let's get started. So with we know that with these pre-trained models, we have seen amazing results on leaderboards and benchmarks. And in fact, I think we're actually struggling coming up with benchmarks that are difficult enough for these models. So since 2 years ago, with these pre-trained transformers, we're surpassing human performance by a large margin. However, even with these amazing results on the leaderboard, once we start to play with these models or put them in production settings, we quickly find that they make catastrophic mistakes that sometimes doesn't really make sense to humans. So here is this well-known reading comprehension example where the model is easily distracted by irrelevant sentence that has high word overlap with a question. And then it decides to change its prediction from the correct answer to some irrelevant span in this distractor sentence. And then in this recent checklist paper, through behavior testing, we can see that even with the seemingly benign transformation of the sentence, such as changing a positive sentence like "I recommend the food" to the negative, to just negate it, like "I can't say I recommend the food," the model fails to change its prediction from positive to negative, which is a little surprising at the beginning. And finally, this phenomenon is not unique to NLP, but a more fundamental problem in all these statistical models. So in this image classification example, if we try to interpret why the model is classifying this image as a wolf, we see that the model is actually relying on the snow in the background to make the prediction. As you can imagine, if now the wolf occurs in some indoor environment, the model would fail to detect that. So, so the common problem underlying all this problem is that the model is relying on some superficial heuristics or shortcuts to make the predictions. Even if the prediction is correct on some benchmarks, they will fail in more realistic settings. So to be more precise, by spurious correlation, what I mean is the predictive rules that works well for certain data sets, which help us get these high accuracies on the leaderboards. But these rules do not hold in general. And I want to go into details up to NLP examples because they will reoccur in this talk. The first is textual entailment, or MLI, where we try to predict whether the premise entails or contradicts the hypothesis. So on this MLI benchmark, people have found that for any sentence with the negation word, the label is very likely to be contradiction. And this is the spurious correlation because in real world, we can easily come up with examples where the hypothesis contains a negation word, but the label is not contradiction. Similarly, on paraphrase identification, on this QKP dataset, whenever two sentences have the same bag of words, they're almost always paraphrases. Like living in Sweden in 1947 is the same as living in 1947 in Sweden. But again, we can come up with counterexamples easily. For example, good person becomes bad, or bad person versus a bad person becomes good. In this case, they use the same set of words, but they're not paraphrases. Now, why do we have these spurious correlations in our data? One prominent source in NLP settings is the so-called annotation bias. So when we collect this MLI data, the way we do it is to give the tracker the premise and ask them to write a sentence that is either true or not true given the premise. So if you think about how can we produce a contradicting sentence given the premise, the easiest way is to just negate the sentence by introducing some negation word here. And if the trackers doesn't try to make their writing strategies diverse, we would end up with a data set where the majority of examples would have this spurious correlation between negation word and the label contradiction. But even if we fix this annotation bias, it's still possible to have spurious correlations just because the data distribution is skewed. For example, we do see more wolves in the snow compared to wolves in the grass. But in this case, we might still want to guarantee some performance for the minority examples on the long tail because of various reasons like safety or fairness. So to summarize, the key problem underlying this spurious correlation is that our data often doesn't have enough coverage or diversity. And the problem that I'm going to focus on in the rest of this talk is that there's some spurious correlation that works for the majority of examples and give us high accuracy on those benchmarks. But at the same time, they don't hold in general. It doesn't generalize to out of distribution examples. So I will introduce three works. The first is the residual fitting, where we design new learning algorithm to focus more on the minority counterexamples. And in the second part, I'll talk about multitasking, where we leverage examples from related tasks to improve generalization from this small amount of counterexamples. And finally, I'll talk about a more recent work on data augmentation. So this is negative results, but I'll explain why this data augmentation approach may not work. So the underlying theme here is that in all of these works, we're trying to make better use of a small amount of counterexamples in our data to improve models' robustness to spurious correlations. I don't see any questions, so I'll continue to the first part. So this is the paper in EMLP workshop in 2019 on learned dataset bias by fixing the residual, and it's joint work with Sheng Zhang and Haohan Wang. Okay, so let's think about this, try to formalize this spurious correlation problem a little bit. So suppose we can decompose the example into some robust feature where for NLP, this mostly means the meaning or semantics of the sentence, and some spurious feature like a single word in the sentence. So suppose we can decompose the feature this way, and we look at the joint probability of the label and our decomposed input, we can rewrite it by the probability of the robust feature or the meaning given the label times the joint probability of the spurious feature and the label. So the important thing to note here is that the robust feature, the conditional probability of the robust feature is invariant, which means it's the same during training and during test, whereas the joint probability of the spurious feature and the label changes at test time. So now if we can disentangle the robust features and the spurious features, the problem is solved because we can just rely on the invariant parts and get a robust feature that doesn't have degraded performance at test time. However, this problem itself, this disentangle problem is quite challenging and it may not be possible without additional prior knowledge. But on the other hand, we often do have some knowledge of the spurious features for specific problems. Like in NLP, we know that we don't want the model to rely on specific words like negation word or single sentiment words. And length could be another spurious feature here. So we can come up with some potential spurious features. So the key idea here is that if we know what are spurious features, then we could focus on learning from examples where the spurious feature and the label are roughly independent. So this is the intuition here. So now let's go through example. So suppose we know that there is some correlation between the negation words and the label for the textual entailment task, and this correlation might change at test time. So let's look at this toy data set where we have 3 examples of this negation word in the hypothesis, but with different labels. So in the ideal setup, we would want the 3 types of examples to have uniform distribution. So in that case, this negation word wouldn't have any strong correlation with the label. However, because of the this annotation bias issue for this specific MLI problem, we end up with data set where the majority of examples contain this exhibit this spurious correlation between negation word and the label. So now if we can detect these type 1 examples, we could focus on the other 2 type of examples where the correlation is much weaker. So now the question becomes, how can we detect whether example is in this majority type where it exhibits some spurious correlation? And we can do this by building a bias classifier. And this uses our prior knowledge on what are the spurious features. So if we know that the negation word is a spurious feature, we could easily build a classifier that only look at the negation word to make the predictions. And now the majority of examples are just the examples where this biased classifier works really well. And once we can detect the types of the examples using this bias prediction, we can intuitively try to downweight the first type of example and upweight the other 2 types to make the distribution more balanced and decorrelate the negation word and the label. Okay, so more formally, we learned this, we use this residual fitting approach. So in the first step, we're basically trying to build this bias classifier and detect whether there's spurious correlation on a certain example. So we learn a bias classifier using some known spurious features like the negation word or the bag-off words. And this is just a standard ERM minimizing the average loss and learn this bias classifier FS. And the second step is the so-called residual fitting process. So we learn this debias classifier by fitting the residuals where it basically means now the output will be the sum of the bias classifier and the debias classifier. And in second step, we fix the output of the bias classifier. And the intuition here is that if the example exhibits the spurious correlation, then the bias classifier would have very low loss on that example. And then in the second stage, it will be ignored by the debias classifier. And then this debias classifier will mainly focus on learning what cannot be predicted by the spurious feature. And if we plug in the cross entropy loss, this is also pretty straightforward. In the first stage, we do MLE and learn this bias classifier PS. And then in the second step, for the output, we just sum the logits from the 2 classifiers. And we can also easily show that in the second step, the probability P of y given x is proportional to the product of the conditional probability given by the bias classifier and the debias classifier. All right, so intuitively, we want to focus on the examples where the spurious correlation doesn't exist. And we can also verify this intuition through some simple gradient analysis. So we can show that in the second step, if we compute the gradient of this residual fitting objective, we can see, we can write that as the MLE gradient, so the standard gradient, plus some bias correction gradient. And this is what makes the model to focus more on the unbiased examples. So suppose we have this example where the negation word is a strong indicator of the label. which means that if we run the bias classifier on this example, the correct label would have probability 1. So in this case, the bias classifier is making a perfect prediction using this negation word feature. In this extreme case, we can show that this bias correction gradient actually cancels the MLE gradient, meaning that the gradient on this example, where the bias classifier is making a perfect prediction, will be 0. And that's effectively removing this example. And on the other extreme, so if you have example where the spurious feature is not predictive at all, meaning that if you run the bias classifier, it gives a uniform distribution over all labels. In this case, where we have this uninformative prediction, we can show that this bias correction gradient actually recovers the MLE gradient. So in this case, where the biased classifier or the spurious feature is not useful at all, we just do a standard MLE update on this example. And if the example is something in between, then we would so this correction gradient would adjust that to downweight depending on how much the downweight the example depending on how much the bias classifier makes a correct prediction. Okay, so let's look at some experiment results. So here for the data, we use the MNLI, the textual entailment data set, and we mainly focus on the hypothesis bias, where the model can just make the correct prediction by only looking at the hypothesis. And the other thing we look at the word overlap bias, which means that if there's a large word overlap between the premise and the hypothesis, then the model tends to predict entailment. And for the model, the biased and the debiased model have the same parameterization. So they're basically the same model. The only difference is the input feature map. So biased model would just look at the hypothesis or the background words, whereas the debiased model have the entire input. And we tried 3 different models, BERT, as well as 2 models in the pre-BERT age that are that have high performance on MNLI task. So this drift is our residual fitting approach, and we also have the MLE as a baseline. So first, we look at the synthetic spurious features. So given an example, we inject some synthetic bias by this cheating label, which is the same as a gold label with some probability. And at test time, this cheating label is randomly assigned. So if the model relies on the cheating label to make prediction, then it would have random performance at test time. Okay, in this figure, we look at performance of 3 different models, and x-axis is the cheating rate, y-axis is the accuracy. So we want to look at as the cheating rate or the bias increases in the training data, how does model performance change? And the baseline is MLE or the orange curve. And then we also use 2 versions of the residual fitting approach. The first is the hypothesis only bias classifier. So the bias classifier only look at the hypothesis, and then we use that to learn the debiased classifier. The second one is a classifier that only looks at the cheating feature. And this is can be think of the Oracle bias classifier because it uses the exact spurious feature that we injected in the example. So the first observation is that as the cheating rate goes above 0.5, meaning that now the majority of examples exhibit this spurious correlation, the performance of MLE drops significantly if you look at the orange curve. Whereas the debiased models, the blue curve and the green curve, maintains a roughly invariant performance as the spurious correlation increases. The other interesting observation is that the prior knowledge on what the spurious feature is really helps. So in this case, if you have the Oracle bias classifier that only uses the cheating feature or this green curve, the overall performance is better than the model that uses the hypothesis only bias classifier. And the reason is that for the hypothesis only classifier, it would downweight, or you can intuitively think of it as removing examples where the hypothesis only classifier works really well. And that some of those could be due to the cheating feature, but some of those could be due to useful features in the hypothesis. So essentially this hypothesis only bias classifier is removing more information compared to this oracle bias classifier. So the overall performance of the hypothesis only model is lower compared to the oracle model. So the precise prior knowledge on what the spurious feature is really important. So in the second part, we look at the word overlap bias. So this is using a challenge data developed by McCoy et al. The spurious correlation here is that if the premise and hypothesis has high word overlap, then it's very likely to be entailment. But then again, we can easily come up with counterexamples. And then they showed that, so they construct this challenge data set with counterexamples and showed that current models work really well on the typical examples where high word overlap implies entailment, but fails completely on this counterexamples, which has high word overlap but are non-entailment. And importantly, this is not due to model capacity, because one might think, okay, these examples are more difficult, so maybe that's why the model fails. But they show that if you just train on a small number of challenge examples, the model can easily achieve very high accuracy. This shows that it's really a data problem, not the model capacity issue. Okay, so here we test the model on both the non-entailment example enhanced, which are the challenge examples or the counter examples, and also the entailment examples. These are the typical examples. And first, okay, so I think the animation here is not quite right. So let me just show all the results and explain it. Okay, the blue bars are the MLE results. So as you can see on the typical example, the performance is really good, but on the challenge example, it's close to 0, especially for these two models. And now, once we use this residual fitting approach, and we have tried 3 different types of bias classifier, the hypothesis only, bag of words, and also some handcrafted bias features. So once we use this residual fitting approach, it doesn't hurt the typical examples, but it improved on the challenge examples, especially when we use this handcrafted bias classifier. So this again shows that your knowledge on this spurious correlation data is really important, because in this handcraft features, we included different spurious features based on prior work, like the negation word, word overlap rate, sentence length, etc. So it has the best performance compared to other device classifiers. Okay, so this is on the out of distribution data, or the challenge data. So we also want to make sure that the model doesn't hurt the in-distribution performance, because we don't want to improve performance on challenge data, but reduce performance on the original benchmark significantly. So let's also look at how does it perform on the original MLI benchmark. So this is the MLE performance, which is the baseline or really the reference here. And so we see that once we train this device classifier, the performance drops a little bit. So this shows that there's some trade-off between robustness and accuracy. And I think this is also observed in adversarial examples. If you try to make the model more robust, then the in-distribution accuracy gets hurt a little bit. But another interesting point here is that the BERT model or the pre-trained models have a good performance for both in-distribution and challenge data. So for these pre-trained models, it seems there's not a significant trade-off between robustness and accuracy. So in the second part, we will investigate a bit more on this pre-training phenomenon. Okay, so to summarize the first part, here, our key observation is that if we have some prior knowledge on what are the spurious correlation in our data set, we can make good use of it. And we design an algorithm to make use of these examples, which does not exhibit strong spurious correlation. And we can essentially upweight or focus more on these clean examples or unbiased examples. But through this debiasing process, we also observe there's some limitation, which is that there is a trade-off between robustness and in-distribution accuracy, which we will investigate more in the second part. But before I move on, I want to check if there's any questions on the first part.
I have one, like a high-level question. So this work is assuming that the data sets are flawed. I guess broadly, whose responsibility do you think it is to fix these issues? Is it just assume that the data sets will always be flawed and like apply these kinds of techniques, or because I also think there could be a lot of improvement on the data set construction side to get rid of many of these issues. I guess not really who's responsible for it, but what in the community, what do you think is, what do you see happening in the future?
Yeah, so I think we tend to think as people working on algorithms, we assume that data set is given and then we just work on algorithms. And if, we tend to think this data problem and algorithm are separate. But I think we should probably start to think about them together. Like now there also works looking at this model in the loop data collection, which try to patch the holes in our model and collect data in a more targeted way. So I think as the, practitioners or people who propose the tasks, it's important for them to specify what are the potential problems in this data set. Then as people who design our algorithms, we can, try to think about how to fix this problems from algorithm perspective. But again, I think in future, I really want to see that data collection and model building or algorithm design are carried out in a more intertwined way, where maybe there could be some loops between the two process.
Yeah, that's cool. I think the model in the loop thing sounds interesting. I don't know if any like major data set that has been created in that way yet, but yeah, it seems like a big, oh yeah, go ahead.
Yeah, so I know Yejin has some work on adversarial filtering, which is along that direction.
Right.
Yeah, that's a good point. Any other questions?
Subindu has a question.
Yeah, hi. I had another overall high-level question as well.
Mm-hmm.
So let's say you have an overall data set on which you're testing your performance. And if you're fixing these spurious relationships, in your model, if it decreases the overall model performance, would you still want to fix the spurious relations? Because you're taking a hit on the overall performance, right?
Yeah, that's a good point. So that's a question of what's the right objective, because if you think about issues like fairness, because these minority examples could be a minority population, and so then how do you weigh the benefit of overall better average accuracy versus a more fair accuracy? So I think this needs to be evaluated for specific tasks.
Got it. I mean, I guess the ideal case would be as a result of fixing these spurious relationships, you're getting an even better overall accuracy, but it looks like that might not always be possible. So, okay.
I agree. So, right. So intuitively, you would think that now the model is using more robust features, it should have better overall performance as well. And I think there are several explanations. So I think one one point is that this spurious correlation, I mean, from the standard machine learning perspective, they're really good features because they're simple, they work well. So if you just think from machine learning perspective, they tend to overfit less, right? So there's no reason that the model shouldn't use these features. And now if you prevent the model from using them, the performance would go down. And the other possibility is that maybe the robust features are just more noisy. So if you want to use robust features, the performance will go down, or you have to collect more data. Okay.
Yeah, thank you.
Cool. So then I guess I'll continue to the second part. Okay, so the second part is based on our technical paper, which try to investigate a little bit on this trade-off between the robust and average accuracy from a more empirical perspective, and specifically focus on the role of pre-training here. And this is a joint work with Li Fu, Girema, and Spandana, while Li Fu was interning at MLFL. Okay, so at the end of the first part, we see that if we use this pre-trained model, it seems that we get both in distribution and challenge data performance. So the first step we did here is just to study this in a more systematic way by scaling up the experiments. So we tested the MNLI for different models, including ECM, which is not pre-trained, and also the set of pre-trained models with different sizes. For the in distribution, as we all know, if you do pre-training, the performance goes up. But then surprisingly, it's also true for out of distribution, or it's challenge data. We also see as you have larger pre-trained model with more pre-training data, the performance goes up. And it's also roughly true for paraphrase identification, not as prominent as MLI, but still we can see some improvement here. So the observation here is that large pre-trained models improve both in distribution and challenge data performance. And then the natural next question is, do these models actually extrapolate out of distribution data, maybe through their more advanced representation of the data? So that's the key question that we want to investigate in this part. So the first observation, again, is that as we see in the first part, even though the majority of examples carry this spurious correlation, there are still a small amount of counterexamples where this spurious correlation doesn't work. And in fact, we also see this happens in the realistic data set as well. So if we think about this word overlap bias, so in MNLI, the majority of examples when the hypothesis is completely a substring of the premise, is almost always entailment. But there are still more than 700 examples where there's 100% overlap, but the label is non-entailment. And similarly in paraphrase identification, we also have about 200 counterexamples where the two sentences have the same bag of words, but the label is not entailment. So our hypothesis here is that maybe pre-training makes the model generalize better from this small amount of counterexamples in the data set. So our first observation is that these minority examples take longer to learn. So this shows the learning curve. The blue line, the red lines are the training accuracy as the epoch increases, and the blue line are the depth set accuracy as the epoch increases. So the important thing is just to look at this is the overall accuracy or the average accuracy. So the average accuracy plateaued after like 3 epochs. This is your number of epochs we do fine tuning. And then this star curve is the accuracy on the minority examples. So even after the average accuracy has plateaued, the minority accuracy continues to increase. And this is also correlated with the model's performance on the challenge data. So this is MLI depth set performance. Again, it plateaus after 3 epochs. But if you look at the performance on the challenge data, it keeps increasing. So, okay, so now we have seen some correlation between the performance on the minority examples in training data and the performance on the other distribution challenge data. So the practical implication here is that for robustness, we might want to fine-tune our model for longer. But this doesn't really explain that these minority examples are the reason that pre-training helps. But I think the second observation really gives a more conclusive answer. So here we try to remove the minority examples in training data, and we see that it hurts the model's robust accuracy on the challenge data. So the x-axis is a percentage of minority examples removed, and y-axis is the accuracy. The orange curve is what happens when we remove random examples. So if you remove random examples of training data for this pre-trained model, it doesn't matter. The performance is almost the same as before. But if we remove the minority examples, we see that the performance on the challenge data drops significantly for all of these pre-trained models. And in fact, once about 6% of data is removed, the accuracy is about 50%, which is the same as the non-pre-trained models. So this shows that the pre-trained models, they cannot just extrapolate to challenge data without seeing any examples, just rely on either the initialization or the representation. They still need to see some counterexamples during training. But the real benefit of pre-training is that it improves robustness to data imbalance. Even you only have a small number of counterexamples, these pre-trained models can generalize from these examples really quickly. Okay, so then there's also a small question we had at the beginning, which is, so we see a large improvement on the textual entailment data, but we don't see much improvement on the paraphrase data sets, the PAWS challenge data. So we also invested that problem a little bit. So here we try to add in some challenge example and see how would that improve the model performance. So for hands, as you can see, if you just add a little bit of the challenge examples, the performance quickly jumps to 100%. Whereas for this PAWS challenge data, the accuracy grows much slowly. So we think the reason is that hands is constructed using templates. So it's probably, if you have examples like that, it's really easy to learn. But PAWS is auto-generated, so it could be harder to learn these examples from a small amount of counterexamples. So perhaps not so surprisingly, different challenge patterns will require different amounts of training data. But the more important implication here is that pre-training is no silver bullet. Like in this case, it's not sufficient for the model to generalize from a small amount of counterexamples. Okay, so how do we improve on that? So let's think about what we have got so far. So we started with this problem of distribution shift. So we have some spurious correlation that works on the majority of examples, but then those minority examples may become majority at test time. So relying on spurious correlation would fail on this test time. And so in the first part, we have this residual fitting algorithm that try to upfit the minority examples in some sense at the cost of the performance other examples. And so here we have also saying that even if we don't change the learning algorithm and just using pre-training, it seems to give us, it seems to allow us to improve performance on minority examples for free just by adding more generic data during the pre-training stage. And so in parallel, there are also other possible fixes. Like there are robust learning algorithms that try to either maximize the worst case performance or enforce the invariance across different environments. So, but in practice, this robust learning algorithms, so similar to the residual fitting approach, also have this problem, this trade-off problem, like they improve out of distribution performance, but then the in distribution performance would hurt a little bit. So in this part, so building upon observation with the improvement from pre-training, we're trying to make better use of generic data to mitigate this robust accuracy trade-off. And in this part, the specific way we use generic data is through this multitasking learning framework, where we leverage data from related tasks. Okay, so the idea here is that we want to improve generalization from a small number of counterexamples or minority examples by transferring knowledge from related tasks. The model is pretty simple. So we have a shared BERT encoder, and on top of that, we have linear task-specific classifiers. For multitask learning, the target task, we're still focusing on textual entailment, where the benchmark is MLI, and paraphrase identification, where the benchmark is Q2P. And for the auxiliary data in multitasking learning, we use this data set, basically some mismatch between MLI and paraphrase tasks. Okay, so let's look at the results. So we look at in-distribution performance and the challenge data performance. So we want to improve on both. And we tested on MLI and paraphrase identification. So this is results for single task learning. And we see that there's some degradation when we move to challenge data. And if we use this multitasking learning procedure, so for in-distribution performance, it doesn't change much, which is consistent with other work on multitasking learning. But for challenge data, it improves the performance, especially for PAWS, quite a bit. And this is using the BERT-based model. And we can see that the benefit from multitasking learning still exists, even if we move to a larger pre-training model, which is Roberta. So here, we didn't hurt in distribution performance, and then we improved the challenge data performance. And next, we also investigate a little on why multitasking learning help. So here, this is the baseline performance, the histogram we have just saying this single task learning and multitasking learning performance. So then we started to do some ablation study by removing examples during training and see how does it affect the testing performance. So now we have two data sources, the target data shown in red, and also the auxiliary data used in multitasking learning. And first, if we remove random examples from either the target data or the auxiliary data, it doesn't change the performance much. So for in-distribution, there's pretty much no difference. For the out-of-distribution, there's some difference, but it might be due to the fact that for out-of-distribution data, we in generally have higher variance. But then if we start to remove the minority examples from the target data, we see a significant drop in the performance of challenge data compared to the other ablations. So which leads us to believe that the way this multitasking learning approach helps is to improve generalization on the minority examples in addition to pre-training. Okay, so in this part, the focus is on mitigate the trade-off between in-distribution and robust accuracy, which we have observed in this robust learning algorithms. And we showed that pre-training helps generalization from minority examples without hurting in-distribution performance. But then here we have to add a lot more generic data for this to happen. Motivated by that, we propose this multitasking learning approach, which uses generic data from other tasks to further improve generalization. Okay, so in the last part, I want to talk about this data augmentation approach, which has been proposed by, which has been mentioned in previous questions, right? So we could fix this from the data perspective. And so the recent works on counterfactual-augmented data from multiple groups like Kaushik and also Matt got us really interested in this approach. So the way this approach works is to edit or intervene on example to discover the robust features. So let's say we have this seed sentence or the original example from the benchmark. This is for sentiment classification. Then in order to figure out which words or sentence are the robust features, we asked Turkers to edit the sentence to flip the label. And so in this case, one possible edit is that you change fascinating to expected, change captivating to mind-numbing. And then by comparing these two examples, we would see that, okay, these words are really what makes the label positive or negative. And right, so basically through this intervention, we can figure out which are causal stance and which are the spurious features. So we got really excited by this, and because we think, okay, if this counterfactual data leads the model to learn robust features, then because robust features are invariant with distribution shift, then we should expect that using this cat data, it should give us better performance out of distribution data. But then the results are mixed. So in Huang et al., they showed that cat doesn't lead to better performance if you want to transfer from SNLI to MLI, and it's the same for the challenge data. And in another paper by Kashabi et al., they showed that on question answering, if we control for the annotation cost and the dataset size for the unaugmented data and the counterfactually-augmented data, then this cat doesn't seem to help. But then again, by the same author, Kaushik et al., they showed that the cat actually discovers useful features, because if we try to noise these additive stance, like replace them with other stance, then the performance got hurt. So which means that stance identified by this cat approach is really useful. So then it seems there is some contradiction. So if they actually reveal useful features, why aren't they helpful for OD generalization? So we can try to explain that through this TWI example. So let's consider this example where we have a TWI data set where we only have two examples. The book is good, the movie is boring. And if you train an IU-based model, and then the word good and boring would have positive and negative weights correspondingly, because so they're in positive and negative examples. But at the same time, the word book and movie would also have negative and positive weights, because we only have two examples. There's no way to differentiate which sets of words are robust or not. So based on these two examples, the book and movie would be the spurious features that the model is relying on. So now if we augment the examples, like we can change good to not good, boring to fascinating, we can successfully debias the book and movie feature, because now they occur in both positive and negative examples. But the problem here is that in the specific example, we also debiased the word good, because through these edits, this good word also occur in both in examples with both labels. So this shows that in this counterfactual data augmentation, if you don't intervene a robust feature, then it cannot be learned from cat, because then this feature would occur in both positive and negative examples. There's no way to learn that. And a more extreme example would be, so in this case, we change boring to fascinating, but suppose we change boring to not boring, then on this augmented data set, the only feature the model is going to learn is this negation word not, which is apparently not desirable. So the importance here is that with this counterfactual augmentation process, you really want your intervention to cover all the different robust features. Otherwise, they're going to be missed by the model. So our hypothesis is that because the current cat data has underdiverse edits, that would limit the effectiveness of this augmentation. And we also try to verify this the real cat data. Because for real examples, it's hard to just look at which stance they change. So we categorize these edits into different perturbation types following some previous work. So essentially quantifier here would mean if you just change the change from 1% to 2%, change the numbers, or negation obviously means to negate the sentence and so on and so forth. So we also have insertion, deletion, etc. But the main point is that this corresponds to different types of edits. Okay, so then we train data generated by a single type of edit, and we want to see how well it generalizes to other type of edits. And the data set size is controlled, so all the training data has the same number of examples. So the first line is the baseline. So here we're not using counterfactual data. This is just the original SNI example. And here's the baseline performance across different augmentations. And then we look at the performance from augmented data. So the first important thing to notice is that as expected on the matched edits, so if both training and testing data are generated by the same type of edits, then CAD achieves the best performance here. However, now if you look at the unmatched test sets, which means we look at whether it generalized to other type of perturbations, the performance are often worse than the baseline using augmented data from SNI. And we also look at how does the accuracy change as we increase the diversity. So here we only look at a single type of edits. How does it generalize to other type of edits? But in this experiment, we try to look at if we increase the edit types during training, how does it affect the OD generalization? So this is SNI baseline having the same number of examples. So all the data set sizes are controlled here. We're just changing the diversity. And as we increase the diversity, the performance keeps going up. So which seems to suggest that the effective data size of this counterfactual augmented data is really the number of robust features that's intervened through this process. And so now the question is, okay, so diversity is important, but you would expect that if you do crowdsourcing, then different people would edit in different ways. So maybe we already have enough coverage or diversity in the CAD data. So we look at as the training data size increases, how does the performance of CAD on OD generalization improves? So here, again, the blue line, the blue curve, shows the performance of SNI. So this is unaugmented data, the standard data. So as the training data size increases, we see the accuracy increases. But then if we increase the number of examples in this counterfactually-augmented data, so this red curve, it seems to plateau much faster than the unaugmented data. But it does have some improvement in the low data regime. Because if you have these pairs of examples, even if you only have a few pairs, it immediately tells the model which are useful features. So in the low data regime, it's really helpful. But as we increase the number of examples, it seems that the diversity doesn't improve correspondingly compared to SNI. And another negative result is that we see this counterfactual augmented data may even exacerbate existing spurious correlations. So we know that in MLI, if we take a sentence that contains a negation word, it's very likely to be a contradiction example. So here we just plot the distribution of the classes conditioned on the fact that the example contains a negation word. For the seed example, the unaugmented example, contradiction is the most likely class given the negation word. And in CAD, it's still true, and it even, it even becomes more severe in this counterfactual augmented data. And similarly, when we look at word overlap, high word overlap examples, in SNI, it's most likely to be entailment example, which again, the problem is being amplified when we shift to this counterfactual augmented data. Okay, so to summarize, in this part, we were initially really excited about this counterfactual data augmentation approach because it is an effective way to identify useful features. However, in practice, because the number of the types of interventions on robust features might be limited, this could also limit what the model can learn. If you don't intervene something, given the pairs of examples, the model cannot learn that. So this means that we probably need better ways to ensure data diversity, like Mohit mentioned. We probably need more innovation in the crowdsourcing procedure. Okay, so I'll conclude my talk here. We talk about 3 different ways to try to make better use of the minority counterexamples in the training data, and learning algorithms. So for now, we still need prior knowledge on the different spurious correlations in the data. And a important future step is to think about how can we automatically discover these majority and minority groups. And because typically we don't always have this prior knowledge on the spurious correlations. And another takeaway is on the data side. The important thing is to improve coverage or diversity for both standard data collection and this counterfactual data collection. But in order to achieve that, we might need more controllable or better crowdsourcing protocols. And I'll stop here. Thank you for listening, and I'm happy to hear any feedbacks or questions.
Thank you so much. Let's unmute and thank the speaker. And feel free to unmute to ask questions. We have a question from Hiba.
Hi. My question was regarding what was discussed initially about spurious correlation. So how do we determine whether a particular word is responsible for spurious correlation? Is it that we just take an example, introduce or remove this word and see if the prediction changes, or does it have to be consistent across for multiple examples? What if I've got a bunch of predictions? Does it have to be change the prediction for all of them, or how many do you observe to just determine whether yes, this is actually inducing a spurious correlation?
Okay, so I think you were talking about this counterfactual augmentation procedure, right? So how do we know? So maybe, in this example, if I change fascinating to expected, the label changes. Maybe another example, if I do the same edits, the label doesn't change, right? Yeah, I think that's a great point. So I think this, the fact that they have to attribute this caudal spans or represent the caudal features as a span of text in the sentence is a bit limited, because here, obviously, this, if you just look at a single word, changing fascinating from a single word expected, it's not necessarily true that the label is definitely negative. The effect of this word apparently also depends on the context.
Exactly.
So in that sense, we can't just say, okay, this span is spurious, but there's some latent robust feature, which, for example, in this case would be the positive sentiment, or whether this is whether this sentence is some negation of another sentence or the tense of this sentence. So we do want this latent features that corresponds to some aspects of the semantics of sentence. But then the challenge there is we cannot surface these latent robust variables, and we can only see that through changes in the sentence form. And I think that's actually one problem that's causing these various weaknesses in the counterfactually augmented data, because much of this is related to the fact that we can only change this, we edit this stance.
Yeah, because I can imagine that I train a model and I'm just trying to understand the reason that the prediction is the way that it is, but I just don't know how I can figure out the token that's causing this or that's causing this spurious correlation if I've just got predictions and it's I'm not the one manipulating it, I've just got the predictions. How do I determine whether this is the token responsible for a spurious correlation?
Yeah, right. So I agree. So to pinpoint that specific spurious feature would be challenging. So yeah, but in general, I guess if you just want to evaluate whether this model is robust, one way is to do this kind of adversarial perturbation or edits. The other is you see if the model generalized to other data sets.
Okay, thank you.
Are there any other questions? I guess I was kind of wondering whether your lab has worked on any other problems besides MLI with this view. Particularly, I was wondering if you have any thoughts about applying it to coreference resolution.
Yeah, that's a good question. So I haven't looked into coreference resolution, but I did think about the text generation because I guess I work on that more. So in text generation, there's also a spurious correlation. Like sometimes the model is ignoring the input context or the source context and just relying on words in the prefix on the target side to predict the next word. And that might be causing different hallucinations that we see in this generation outputs. So yeah, so you're right that it's definitely not limited to MLI or paraphrase detection. I think this is a more broad problem for many tasks. Like in coreference resolution, I think many people look at this gender bias. So that's one the spurious correlation, right? Yeah.
Yeah, I think there's so much potential. It's really awesome. I'll let Shreya go ahead.
Hi, so I was just wondering, do you think it's possible or desired even to like establish some kind of standards for either creating data sets or when developing models that, you know, there should be these things that should be checked for spurious correlation, like maybe negation is something that might pop up a lot, or do you think that's something that can be done or should be done, that every model or data set should be checked against certain I don't know, standards or baselines?
Yeah, so I'll answer about the evaluation part first. So I definitely agree that static benchmarks are not so useful now. As we can see, if you have a benchmark, the model can perform really well. And also, even for this static challenge data, it's kind of ad hoc in the sense that, okay, someone observed, okay, here's one word order bias, here's one negation word bias, and I'm going to build some challenge data specific for this spurious correlation. And that's, even if the model performs well on this specific challenge data sets, it might fail on some unknown spurious correlations. So I think we probably need some model in the loop, a human in the loop evaluation. Like there's now this dynamic or DynaBench, which put up a model that asks humans to start to play with the model and see if there's any examples that the model might fail on. So that might be a more sustaining way to detect these different spurious correlations in the model. Or we could even, yeah, so now that I'm thinking about this, I think maybe it's even possible to have another generator that generates different types of examples and then try to fail the model. It's more in an adversarial way.
Thank you so much. I guess I also want to let you take a little break before your next meeting starts. So if there are no more questions, maybe we can unmute and thank Professor He again. Thank you so much. This was such a great talk.
Thank you. Yeah. I'll see you in the one-on-ones.